Today we're going to talk about pullbacks. Pullbacks are another form of quite simple limit, at least simple compared with the wild things that we'll get later. And they're very useful, and in fact you've seen them before. I promise you have, you just perhaps didn't know that that's what they were. So let's just see what a pullback is for a start. Now, the data that you start with is a bit more complicated than we've had for our limits before. You start with a pair of maps. So you have one map here and one map here in a category. And a pullback is, you have a vertex U and you have a pair of projection maps. So you can think of this a bit like being a product, and we'll see later that it's closely related to products. But where with products we had just an A and a B, and we didn't have this bit, and we got from our limit a vertex together with a pair of projection maps. It's the same kind of thing now. We have a vertex, a pair of projection maps, which I'll call P and Q. Now this diagram has to commute. So this diagram commutes, and it's the best possible one among all such diagrams. So this is going to have a universal property, and as usual the universal property says it's the best one. How do we express that? We say given any other one, there's a unique factorization. So you should be starting to recognize this form of universality now. So what's another one? We've got to say given another one. So another one is a square like this. Now the F and the G parts are the bits that are sort of fixed whenever we're thinking about this particular kind of limit. So another one is another vertex V and another pair of projection maps, let's call them S and T, such that the outside square commutes. So given that, there has to be a unique factorization here, which I'll call H, making both this triangle and this triangle commute. So perhaps I should write a bit more. Well, I'll just indicate over here. So again, you've got to read this as a kind of dynamic diagram. So what this is saying, so pullback, we often call this a pullback of G along F, because you can imagine that G is a thing over here, and you're pulling it back along F until it gets all the way to here. Of course, there's some symmetry in this definition, so you can also think of this as F being pulled back along G. So this is sometimes called a pullback of G along F. It's also a pullback of F along G by symmetry. We sometimes also write it like this: A cross B over C, and I'll explain a bit more where that notation comes from in a second. Anyway, this pullback is given by a commuting square so I suppose I should draw it, but I can't really be bothered. But it's the commuting square that's got U up there and A, B and C here. And then we have the universal property such that for all other squares, so that's the outside now, let me just draw this quickly like this. So for all commuting squares like that, commuting, there exists a unique H like that, making the diagram commute. What else is there to say about this? Well, probably first we should immediately see an example of what kind of thing you get when you do this. So when you do this to sets, something quite simple and quite nice comes out of it. What should I take off? I'll take this off. So in set, in the category of sets and functions, what we're going to get, so we've got a function here, and we've got a function here as well. And what we've got to produce is some set together with projection maps that make these commute and in the best possible way. So if you think about it, maybe you shouldn't think about it, let's try thinking about it. If you think about it, if these maps weren't there, you would just take the product, and this would be the set of ordered pairs. If you take the Cartesian product, you get a set of ordered pairs A, B. right? A in here and B in there. But we've got this extra condition now, which is that when we map down to there and we map down to here, we've got to land in the same place. So all we're going to do is restrict to those pairs A and B that actually land in the same place when you hit them with F and G. So what we're going to get over here is the set of pairs A comma B in A cross B such that F of A equals G of B. Now, for the universal property, what we've got to do is we've got to take another set V equipped with, I'm crashing, never mind. Equipped with functions S and T making the outside commute, we've got to make some morphism going down here. Now, to construct this morphism, it's very similar to what we did with products, she said, desperately hoping that it is very similar to what we did with products. So you've got to say, okay, let's have a little look at a little V in this set here. Now, it lands somewhere over here and it lands somewhere over here. But what we've got to do is we've got to send it to some pair here in such a way that it will make the square commute. Now, what pair of objects in A and B could we possibly send it to? Just stare at this for a second. How could you possibly dream up an object in A and an object in B starting from this little V over here? Well, there's one thing you can do. You can hit it with S, which produces you an object in A, and you can hit it with T, which produces you an object in B. So that's the most obvious thing you could do. And because it's the most obvious, you hope that it's going to be the right one. So now I've completely messed up this diagram. What should I do? Help, help, help. Okay, this morphism I'm constructing here is going to be called H. So H is going to go from, it's going to take V, and it's going to send it to the pair S of V, T of V. Now, this is still a thought experiment, right? Because we don't know yet that that's actually landed in the right place. We know that if we're going to make these triangles commute, then this jolly well has to be what H does, because otherwise it's all going to go wrong. So if it exists, then it has to be that, so that's the uniqueness. Now we can see whether this actually does land inside this, this set here. So how do we tell if it's landed in this set? We see if this condition holds. So we need to check that f of the first thing, f of S of V, equals G of the second thing. That's the condition that shows that it's really in this pullback. And now, is this true? Why is this true? Well, oh look, F composed with S is this side, and T composed with G is this side. And this commutes by the assumption we put in the first place, because we said, given any V together with functions S and T making the outside commute. So this commutes, this is true since the outside of the diagram commutes. And so we've now constructed something that really is a unique factorization, showing that that really was the correct thing to take as the pullback of those two things. Now, this is sometimes also called a fibered product. And you can see why, because it's sort of like a product except that it's fibered, because you're taking the fibers sort of over each of the individual elements of C. You're taking the things that actually land in the same place there. This is sometimes also called a Cartesian square, especially in French. And for this reason, when you see things that are Cartesian functors, Cartesian monads, Cartesian natural transformations, Cartesian categories, that's often something to do with behaving well with respect to pullbacks. And next time we'll look at the dual and possibly another example. Now we're going to talk about pushouts, which are the dual of pullbacks. As you've probably worked out by now, all limits and co-limits come in kind of pairs because there's always the dual case. And so far, the examples of limits that we've had have been terminal objects and products and pullbacks, and the examples of co-limits that we've had have been initial objects, co-products, and now we're going to see pushouts. Now, how do you tell which ones are the limits and which ones are the co-limits? Well, one answer is they're really just the same thing, one's in the opposite category, blah, blah, blah. But another answer is it's about which direction your universal property is going in. So I'll say a little bit more about that once we've done pushouts. Now, pushouts are the dual of pullbacks. So all we have to do is turn all the arrows around in this diagram and use exactly the same definition. However, I'm not just going to plunge in and mangle this diagram because I want to leave that one there so we can compare it. And because usually pushouts are written the other way to keep our flow going this way down through the world rather than flowing sort of backwards up through the world. So what's a pushout? Well, we're going to start with the following data. Perhaps I shouldn't have used such similar notation. Oh well. So we start with maps going to A and to B from the same place. And so what's our pushout going to be? It's going to give us a vertex here, U, the universal one, together with a pair of insertion maps like this, making this diagram commute. So this is a commuting square. And now we need a universal property, which is that this one's got to be the best one out of all those commuting squares. So we're going to say, given any other one, together with, so given any V together with maps S and T making the outside of this commute, there has to be a unique factorization in that direction. So there is a unique factorization H. So the way to remember which way around this factorization goes is you've got to think, okay, this is your universal one. And what you've got to say is that every other one factors through the universal one, which means that the universal one is kind of a factor of the other one. You're taking the universal one and you have to sort of stick a bit onto it, multiply it by something in order to get the non-universal one. And the same is true here. The universal one is the smaller one, as it were, and so to get the outside part, you've got to compose it by another morphism in order to get the outside part. And if you think about it like that, you can never get your thing going in the wrong direction. But secretly, I just always visualize this diagram for a pullback and that one for a push-up, and then I always know which way around I'm going. Oh, by the way, if this is a pullback square, we quite often write a little thing like that in the top left-hand corner. And for a push-out, to indicate a push-out, we often write a little thing like that in the bottom right-hand corner. Now you're probably wondering what a push-out is in sets. That's an excellent question. Well done, good question. So what we're going to do, we're going to have a look at push-outs in sets. So if these are sets and functions, the push-out here, what it's going to be, so you should think to yourself for a second, well, it's going to be a bit like a co-product. Remember here what we did was we took the product and then we modified it a bit. So what we're going to do here is we're going to take the co-product and we're going to modify that a bit. So co-product of what? Just hallucinate away this part of the diagram, and you've just got an A and a B and the co-product here. So that's like taking the disjoint union of A and B. So we're going to start by taking the disjoint union of A and B. However, we don't stop there because we've got this extra condition, right? It's got to, this part of the diagram has to commute, which means that we can't just stick A and B together, because imagine this, there's some little element in C, it goes somewhere in A, goes somewhere in B, now they both land in the disjoint union. Oh no, they haven't landed in the same place. So how do we fix that? Well, we just force them to be the same. So what we do is we quotient out by an equivalence relation. Which equivalence relation? Well, exactly the one we need, of course. The one that is generated by, so we quotient out by this equivalence relation, generated by f of c has to be equivalent to g of c for all c in C. Now, when we say generated by, we may have to add some, these won't be all the relations that we have, right? Because if f of c1 is equal to f of c2, then that'll create some more things that we need. So let me write this over here. So if we have f of c1 is actually equal to f of c2, then according to this equivalence relation, f of c1 is going to have to be equivalent to g of c1, and f of c2 is going to have to be equivalent to g of c2, But because this is an equivalence relation, that means that these two things will have to be equivalent to each other as well. So that's going to be another one. You see, this is now G of C1 is equivalent to G of C2. That's not something that was actually explicitly stated in here. So how do you say what's the equivalence relation generated by these things? Well, it's the pushout. Perhaps I'll move swiftly on now. What was I going to say apart from that? Oh yes, there's my favourite pullback and pushouts diagram, which I would now like to put here. By the way, pullbacks and pushouts are very good prototype examples of limits and co-limits. So if you sort of see other limits and co-limits, for example, in set, then they work pretty much like pullbacks and pushouts do. Now, consider sets. Well, why am I writing that on the board? I don't know. I'll just do this instead. So suppose we've got sets A and B. If we put the intersection here, and we put the union here, this is a rather pleasing diagram. The intersection has a natural inclusion into A, and it has an inclusion in B. And A has an inclusion into this union. This isn't a disjoint union, it's a union. And B also has an inclusion in here. And this diagram is in fact both a pullback and a pushout, which is rather satisfying, is it not? I think that's all I'm going to say for now.